Okay, hello everyone. My name is Yuyan. To present our work on modeling Reachability types with logical relations. This is the joint work with Songlin, Guannan, Oliver, and Tiark. Guannan now is a sitter at the Tufts. Okay. This doesn't work. What this doesn't? Okay. So, as we all know that ownership system track resources, especially memory resources. After 20 decades research on ownership type systems, Rust finally make a successful adoption of ownership in system programming languages. So now the challenge is how to adopt ownership for languages that combine object-oriented feature and hierarchical functions for a language like Scala. Okay, sorry. So how are we going to, what are the venues to address these challenges? So the promising venue, I guess, now is that we switch the restrictive properties such as unique owners to descriptive properties such as tracking reachabilities. Therefore, our prior work proposed reachability types, track sharing, and separation in hierarchical languages. Compared approach of Rust, we start from a liberal foundation, just tracking reachabilities and add constraints such as uniqueness on top of it. So we believe this is a suitable way to integrate ownership with hierarchical languages. So now let's have a quick overview of reachability types. So our types track variables in type qualifiers. Here the type means the evaluation result from T can be reached by variable x, y, z. But other locations, but not other locations refer to other variables. One of the key ideas of reachability types is to allow user to specify separation. Here, the type tells us the two variables reach separate locations. Now, the type of the qualifiers on the argument here, the diamond, says the reachable location from arguments are separated from the reachable location from the function. Now we call the function with C1 is type error, call C2 is okay. So this is because we have the guarantee that our syntactic separation guarantee semantic separation. So based on our previous result, we proved the syntactic type soundness by using progress and preservation. Also, we proved the preservation of separation. Of course, we are not the only one who pursue these directions. In Scala's team, they designed capturing types, and they have the real-world implementation. Now, the open question, although we have some good result, and now the open question is, so what are the stronger metatheoretic properties such as semantic soundness, termination, effect safety, and equational theory? So in this talk, we start from the standard logical relation for the simply typed lambda calculus with first-order references. We augmented with internal invariants to track the flow of store locations without restricting expressiveness. Then we rediscover reachability types by propagating selected choices to user-facing qualifiers. So we use the, let's look at logical relations. This allows us to define some properties about types. So now let's look at the value interpretation of function types. So it tells us the closure value is valid at store typing sigma if we have some argument satisfy the argument type at some future store typing. And then we evaluate the term will have some value, the value satisfy the result type. So this is the function type, and then because our program, the store always grows monotonically, so we use the store typing extension to model it. So this is consistent with the program semantics. And then we also, of course, we need to define some other, like semantic interpretation of terms as well. And suppose we have all the definition, then we can prove the fundamental theorem, which says syntactic type soundness syntactic judgment implies semantic judgment. And then, of course, this gives us some very stronger result. And then, however, the kind of the property that we can entail is still limited. For example, let's look at this example. The program allocated two references, and then they have a function. The function updates one of them. Then we have the assertion one to say the another value stored in the location are preserved. So with the logical relation we just saw, we cannot prove it. And also, the assertion is an unsafe feature because statically we cannot not guarantee the assertion is always true. So this is, but however, this is an unsafe feature used in a safe way. So how can we? What's the problem is we lack of some local reasoning. So, but well, we all know some existing approach exists. For example, sufficient logic. So inspired by sufficient logic is basically tell us we can have localized the store location to whatever the proof matters. So now instead of your store typing extension, we define relational store typing. It allows us to localize to the locations that are reachable from given values. Now we can use the relational store typing to define our function interpretation of functions. Now the sigma prime is will only related to sigma with the location reachable from the closures. And then the argument value is valid. Then we prove the program doesn't run, we got some values. So basically this already gives us what's the statement in the Reynolds paper. And then we can say a few more about some reachable information of the function argument result and the value preservation property, which is just a frame property. So, sorry. And then this is kind of a lot of formula. So now let's have a summary of what actually those formula tells. Those formulas just actually a bunch of semantic property. So basically, if we can have talk about some reachability information, we can say the argument overlap with either the closure or not the part of the closure. So if it's not part of the closure, we call it contextually fresh. Similar for result, it can be either overlap with the closure or the argument of fresh allocated location during the evaluation of the term. And then we can talk about observable effects, which are values stored not in the argument or the function. Those values will be preserved. It's something like a sufficient logic frame rule. And then now with this kind of semantic property, let's look at the identity function. Basically, we pass value A, we want to get some result that reach A. We pass value B, we want to get the result reach B. If we pass some fresh value, we want to get the result must be fresh. So this is just STLC. So the idea is, what if we expose this kind of semantic reachability information in the types? So this is exactly the motivation we have for the defined reachability types. So now let's look at the function type in reachability types. Our function type is qualifier dependent type. So basically, instead previously we just showed some summaries, some desired property we want to have. Now we are showing the qualifiers that actually can express this kind of information. So we can use some variable to say the argument overlap something in the environment, or use this symbol to say it's overlap with anything captured by the closure. Our diamond is the fresh. Similar for the result. And then we can have observable effects, which are not touched by function and argument. And then we can just change our logical relation. Now we just interpreted of our function qualifiers. We got the desired reachable information defined in the logical relations. Now let's look at this identity function again. Now we don't even have to look at the term, but just look at the type. we know that this is that's what it is. Basically, the type tells us you pass something in, then I will pass something out. So it gives us a precise reachable information. So then we can achieve some parametric parametricity without explicit quantifiers. And then we prove the semantic soundness and the termination. And then we also define binary logical relation and to talk about the contextual equivalence. And we prove some two computation can be reordered if their observations are separate. So this simple program, basically, if two programs they work on separate memory locations, they can be swapped. Of course, this is kind of not desired because this doesn't have to be this way. We can do it more precise. Therefore, we add effect qualifiers to the function type. So the epsilon is just a latent effect. And then the argument qualifier, result qualifier are the same. And then the effect qualifier have the same expressiveness as argument qualifier and the result qualifiers. Then we can prove the reordering by using the effects. It's basically said the read can be overlap, and then A cannot read A, please read. So basically, we see this problem, so we can prove their equivalence. So now let's say we can, by using the effects information, we can prove more reordering rules, enable create more optimization opportunities. So as a summary, today we present our semantic model of reachability types. We define the semantic type soundness, we got the termination, effect safety, and prove the program equivalence. All the results have been proved in Calc and can be found online. And also in our reachability types, we have some more recent result. So in the paper, we have the higher order store reference, but we can prove terminate, and which is kind of a surprise because we have some limitation in our type expressions. So in the Davis paper, we address this limitation to allow cycles. And then if you are asking about the annotation overhead, then we have bidirectional typing. In addition, we can leverage reachability qualifiers to do group reasoning like arena and to do memory management. And at the beginning of the talk, we said we want to build a liberal foundation and add constraint on top of it. So then today I only talk about the first part. Then the second part is actually can be found by Davis paper, the allocation and ownership transfer. And then also we can, with the ownership transfer and something, and then we can have some, we can build the flow sensitive system to talk about type state. And then we can use that to prove the correctness of API use. And then today I just somehow implicitly say we have some encoding for capability and the effect system. But I don't have the formal connection. And then in the latest work, we have the formal connection. We also have a solution for affordable effect polymorphism without for our quantifications. So please take a look at our latest work. Can be found on the website.
All right, thank you. We may have time for one very short question. Anyone? All right. Otherwise, let's thank the speaker again.